Chapter 2. The Mathematical Building Blocks of Neural Networks. This chapter covers a first example of a neural network, tensors and tensor operations, how neural networks learn via backpropagation and gradient descent. Understanding deep learning requires familiarity with many simple mathematical concepts: tensors, tensor operations, differentiation, gradient descent, and so on. Our goal in this chapter is to build up your intuition about these notions without getting overly technical. In particular, we'll steer away from mathematical notation, which can introduce unnecessary barriers for those without any mathematical background and isn't necessary to explain things well. The most precise, unambiguous description of a mathematical operation is its executable code. To provide sufficient context for introducing tensors and gradient descent, we'll begin the chapter with a practical example of a neural network. We'll then go over every new concept that's been introduced point by point. Keep in mind that these concepts will be essential for you to understand the practical examples in the following chapters. After reading this chapter, you'll have an intuitive understanding of the mathematical theory behind deep learning, and you'll be ready to start diving into Keras and TensorFlow in Chapter 3. Section 2.1. A first look at a neural network. Let's look at a concrete example of a neural network that uses the Python library Keras to learn to classify handwritten digits. Unless you already have experience with Keras or similar libraries, you won't understand everything about this first example right away. That's fine. In the next chapter, we'll review each element in the example and explain them in detail. So don't worry if some steps seem arbitrary or look like magic to you. We've got to start somewhere. The problem we're trying to solve here is to classify grayscale images of handwritten digits, 28 by 28 pixels, into their 10 categories, 0 through 9. We'll use the MNIST dataset, a classic in the machine learning community, which has been around almost as long as the field itself, and has been intensively studied. It is a set of 60,000 training images plus 10,000 test images assembled by the National Institute of Standards and Technologies, the NIST in MNIST, in the 1980s. You can think of solving MNIST as the hello world of deep learning. It's what you do to verify that your algorithms are working as expected. As you become a machine learning practitioner, you'll see MNIST come up over and over again in scientific papers, blog posts, and so on. You can see some MNIST samples in Figure 2.1. Note: in machine learning, a category in a classification problem is called a class. Data points are called samples. The class associated with a specific sample is called a label. You don't need to try to reproduce this example on your machine just now. If you wish to, you first need to set up a deep learning workspace, which is covered in Chapter 3. The MNIST dataset comes preloaded in Keras in the form of a set of 4 NumPy arrays. Train_images and train_labels form the training set, the data that the model will learn from. The model will then be tested on the test set, test_images and test_labels. The images are encoded as NumPy arrays, and the labels are an array of digits ranging from 0 to 9. The images and labels have a one-to-one correspondence. Let's look at the training data. And here's the test data. The workflow will be as follows. First, we'll feed the neural network the training data, train_images and train_labels. The network will then learn to associate images and labels. Finally, we'll ask the network to produce predictions for test_images, and we'll verify whether these predictions match the labels from test_labels. Let's build the network. Again, remember, you aren't expected to understand everything about this example yet. The core building block of neural networks is the layer. You can think of a layer as filter for data, or some data goes in and it comes out in a more useful form. Specifically, layers extract representations out of the data fed into them. Hopefully, representations that are more meaningful for the problem at hand. Most of deep learning consists of chaining together simple layers that will implement a form of progressive data distillation. A deep learning model is like a sieve for data processing, made of a succession of increasingly refined data filters, the layers. Here, our model consists of a sequence of two dense layers, which are densely connected, also called fully connected neural layers. The second and last layer is a 10-way softmax classification layer, which means it will return an array of 10 probability scores summing to 1. Each score will be the probability that the current digit image belongs to one of our 10-digit classes. To make the model ready for training, we need to pick 3 more things as part of the compilation step. An optimizer, the mechanism through which the model will update itself based on the training data it sees so as to improve its performance. A loss function, how the model will be able to measure its performance on the training data and thus how it will be able to steer itself in the right direction. Metrics to monitor during training and testing. Here, we'll only care about accuracy, the fraction of the images that were correctly classified. The exact purpose of the loss function and the optimizer will be made clear throughout the next 2 chapters. Before training, we'll process the data by reshaping it into the shape the model expects and scaling it so that all values are in the 0 to 1 interval. Previously, our training images were stored in an array of shape 60,000 by 28 by 28 of type uint8, with values in the 0 to 255 interval. We'll transform it into a float32 array of shape 60,000 by 28 times 28, with values between 0 and 1. We're now ready to train the model, which in Keras is done via a call to the model's fit method. We fit the model to its training data. 2 quantities are displayed during training: the loss of the model over the training data, and the accuracy of the model over the training data. We quickly reach an accuracy of 0.989, or 98.9% on the training data. Now that we have a trained model, we can use it to predict class probabilities for new digits, images that weren't part of the training data, like those from the test set. Each number of index I in that array corresponds to the probability that digit image test_digit 0 belongs to class I. The first test digit has the highest probability score, 0.9999906, almost 1, at index 7. So, according to our model, it must be a 7. We can check that test label agrees. On average, how good is our model at classifying such never-before-seen digits? Let's check by computing average accuracy over the entire test set. The test set accuracy turns out to be 97.8%. That's quite a bit lower than the training set accuracy, which was 98.9%. This gap between training accuracy and test accuracy is an example of overfitting. The fact that machine learning models tend to perform worse on new data than on their training data. Overfitting is a central topic in Chapter 3. This concludes our first example. You just saw how you can build and train a neural network to classify handwritten digits in less than 15 lines of Python code. In this chapter and the next, we'll go into detail about every moving piece we just previewed and clarify what's going on behind the scenes. You'll learn about tensors, the data storing objects going into the model, tensor operations, which layers are made of, and gradient descent, which allows your model to learn from its training examples.
Section 2.2. Data Representations for Neural Networks. In the previous example, we started from data stored in multidimensional NumPy arrays, also called tensors. In general, all current machine learning systems use tensors as their basic data structure. Tensors are fundamental to the field, so fundamental that TensorFlow was named after them. So what is a tensor? At its core, a tensor is a container for data, usually numerical data. So it's a container for numbers. You may already be familiar with matrices, which are rank 2 tensors. Tensors are a generalization of matrices to an arbitrary number of dimensions. Note that in the context of tensors, a dimension is often called an axis. Section 2.2.1 Scalars. Rank 0 tensors. A tensor that only contains one number is called a scalar, or scalar tensor, or rank 0 tensor, or 0D tensor. In NumPy, a float32 or float64 number is a scalar tensor, or scalar array. You can display the number of axes on a NumPy tensor via the ndim attribute. A scalar tensor has 0 axes, ndim equals 0. The number of axes of a tensor is also called its rank. Here is a NumPy scalar. Section 2.2.2 Vectors. Rank 1 tensors. An array of numbers is called a vector, or rank 1 tensor, or 1D tensor. A rank 1 tensor is said to have exactly one axis. Following is a NumPy vector. This vector has 5 entries, and so is called a 5-dimensional vector. Don't confuse a 5D vector with a 5D tensor. A 5D vector has only one axis and has 5 dimensions along its axis, whereas a 5D tensor has 5 axes and may have any number of dimensions along each axis. Dimensionality can denote either the number of entries along a specific axis, as in the case with our 5D vector, or the number of axes in a tensor, such as a 5D tensor, which can be confusing at times. In the latter case, it's technically more correct to talk about a tensor of rank 5, the rank of a tensor being the number of axes, but the ambiguous notation 5D tensor is common regardless. Section 2.2.3 Matrices, or rank 2 tensors. An array of vectors is a matrix, or rank 2 tensor, or 2D tensor. A matrix has 2 axes, often referred to as rows and columns. You can visually interpret a matrix as a rectangular grid of numbers. This is a NumPy matrix. The entries from the first axis are called the rows, and the entries from the second axis are called the columns. In the previous example, 5, 78, 2, 34, 0 is the first row of X, and 5, 6, 7 is the first column. Section 2.2.4 Rank 3 and higher rank tensors. If you pack such matrices into a new array, you obtain a rank 3 tensor, or 3D tensor, which you can visually interpret as a cube of numbers. Following is a NumPy rank 3 tensor. By packing rank 3 tensors into an array, you can create a rank 4 tensor, and so on. In deep learning, you'll generally manipulate tensors with ranks 0 to 4, although you may go up to 5 if you process video data. Section 2.2.5 Key Attributes. A tensor is defined by 3 key attributes. Number of axes, or rank. For instance, a rank 3 tensor has 3 axes, and a matrix has 2 axes. This is also called the tensor's ndim in Python libraries such as NumPy or TensorFlow. Shape. This is a tuple of integers that describes how many dimensions the tensor has along each axis. For instance, the previous matrix example has a shape of 3, 5 surrounded by parentheses, and the rank 3 tensor example has a shape of 3, 3, 5 surrounded by parentheses. A vector has a shape with a single element, such as 5, surrounded by parentheses, whereas a scalar has an empty shape of an open-closed parentheses. Data type, usually called dtype in Python libraries. This is the type of data contained in the tensor. For instance, a tensor's type could be float16, float32, float64, uint8, and so on. In TensorFlow, you are also likely to come across string tensors. To make this more concrete, let's look back at the data we processed in the MNIST example. First, we load the MNIST dataset. Next, we display the number of axes of the tensor train_images, the ndim attribute. Here's its shape. And this is its data type, the dtype attribute. So what we have here is a rank 3 tensor of 8-bit integers. More precisely, it's an array of 60,000 matrices of 28 by 28 integers. Each such matrix is a grayscale image with coefficients between 0 and 255. Let's display the fourth digit in this rank 3 tensor using the matplot library, a well-known Python data visualization library which comes pre-installed in Colab. See Figure 2.2. Naturally, the corresponding label is the integer 9. Section 2.2.6. Manipulating tensors in NumPy. In the previous example, we selected a specific digit alongside the first access using the syntax train_images index of I. Selecting specific elements in a tensor is called tensor slicing. Let's look at the tensor slicing operations you can do on NumPy arrays. The following example selects digits number 10 to number 100. Number 100 isn't included, and puts them into an array of shape 90, 28, 28, surrounded by parentheses. It's equivalent to this more detailed notation, which specifies a start index and stop index for the slice along each tensor axis. Note that colon is the equivalent to selecting the entire axis. In general, you may select slices between any two indices along each tensor axis. For instance, in order to select 14 by 14 pixels in the bottom right corner of all images, you would do this. It's also possible to use negative indices, much like negative indices in Python lists. They indicate a position relative to the end of the current axis. In order to crop the images to patches of 14 by 14 pixels centered in the middle, you'd do this. Section 2.2.7. The notion of data branches. In general, the first axis 0 because indexing starts at 0, in all data tensors you'll come across in deep learning will be the samples axis, sometimes called the samples dimension. In the MNIST example, samples are images of digits. In addition, deep learning models don't process an entire data set at once. Rather, they break the data into small batches. Concretely, here's a batch of our MNIST digits with a batch size of 128. And here's the next batch. And the nth batch. When considering such a batch tensor, the first axis, axis 0, is called the batch axis or batch dimension. This is a term you'll frequently encounter when using Keras and other deep learning libraries. Section 2.2.8. Real-world examples of data tensors. Let's make data tensors more concrete with a few examples similar to what you'll encounter later. The data you'll manipulate will almost always fall into one of the following categories. Vector data, rank 2 tensors of shape samples, features, where each sample is a vector of numerical attributes, or features. Time series data or sequence data. Rank 3 tensors of shape samples, timestamps, features, where each sample is a sequence of length time steps of feature vectors. Images. Rank 4 tensors of shape samples, height, width, channels, where each sample is a 2D grid of pixels and each pixel is represented by a vector of values, or channels. Video. Rank 5 tensors of shape samples, frames, height, width, channels, where each sample is a sequence of length frames of images. Section 2.2.9. Vector data. This is one of the most common cases. In such a data set, each single data point can be encoded as a vector. and thus a batch of data will be encoded as a rank 2 tensor, that is, an array of vectors, where the first axis is the samples axis and the second axis is the features axis. Let's take a look at two examples. An actuarial data set of people, where we consider each person's age, gender, and income. Each person can be characterized as a vector of 3 values, and thus an entire data set of 100,000 people can be stored in a rank 2 tensor of shape 100,000, 3 surrounded by parentheses. A data set of text documents where we represent each document by the counts of how many times each word appears in it out of a dictionary of 20,000 common words. Each document can be encoded as a vector of 20,000 values, one count per word in the dictionary. And thus, an entire data set of 500 documents can be stored in a tensor of shape 500, 20,000 surrounded by parentheses. Section 2.2.10. Time series data or sequence data. Whenever time matters in your data, or the notion of sequence order, it makes sense to store it in a rank 3 tensor with an explicit time axis. Each sample can be encoded as a sequence of vectors, a rank 2 tensor, and thus a batch of data will be encoded as a rank 3 tensor. See Figure 2.3. The time axis is always the second axis, axis of index 1, by convention. Let's look at a few examples. A data set of stock prices. Every minute we store the current price of the stock, the highest price in the past minute, and the lowest price in the past minute. Thus, every minute is encoded as a 3D vector. An entire day of trading is encoded as a matrix of shape 390, 3 surrounded in parentheses. There are 390 minutes in a trading day, and 250 days worth of data can be stored in a rank 3 tensor of shape 250, 390, 3 surrounded in parentheses. Here, each sample would be 1 day's worth of data. A data set of tweets, where we encode each tweet as a sequence of 280 characters out of an alphabet of 128 unique characters. In this setting, each character can be encoded as a binary vector of size 128, an all zeros vector except for a 1 entry at the index corresponding to the character. Then, each tweet can be encoded as a rank 2 tensor of shape 280, 128, surrounded by parentheses. And a data set of 1 million tweets can be stored in a tensor of shape 1 million, 280, 128, surrounded by parentheses. Section 2.2.11. Image data. Images typically have 3 dimensions: height, width, and color depth. Although grayscale images, like our MNIST digits, only have a single color channel and could thus be stored in rank 2 tensors. By convention, image tensors are always rank 3, with a one-dimensional color channel for grayscale images. A batch of 128 grayscale images of size 256 by 256 could thus be stored in a tensor of shape 128, 256, 256, 1, surrounded in parentheses. And a batch of 128 color images could be stored in a tensor of shape 128, 256, 256, 3, surrounded in parentheses. See Figure 2.4. There are 2 conventions for shapes of image tensors: the channel's last convention, which is standard in TensorFlow, and the channel's first convention, which is increasingly falling out of favor. The channel's last convention places the color depth axis at the end, samples, height, width, color underscore depth, surrounded in parentheses. Meanwhile, the channel's first convention places the color depth axis right after the batch axis, samples, color underscore depth, height, width, surrounded in parentheses. With the channel's first convention, the previous examples would become 128, 1, 256, 256 surrounded in parentheses, and 128, 3, 256, 256 surrounded in parentheses. The Keras API provides support for both formats. Section 2.2.12. Video data. Video data is one of the few types of real-world data for which you'll need rank 5 tensors. A video can be understood as a sequence of frames, each frame being a color image. Because each frame can be stored in a rank 3 tensor, height, width, color underscore depth surrounded in parentheses, a sequence of frames can be stored in a rank 4 tensor, frames, height, width, color underscore depth surrounded in parentheses. And thus, a batch of different videos can be stored in a rank 5 tensor of shape, samples, frames, height, width, color underscore depth surrounded in parentheses. For instance, a 60-second 140 by 256 YouTube video clip sampled at 4 frames per second would have 240 frames. A batch of 4 such video clips would be stored in a tensor of shape 4, 240, 144, 256, 3 surrounded in parentheses. That's a total of 106,168,320 values. If the D-type of the tensor was float32, each value would be stored in 32 bits, so the tensor would represent 405 megabytes. Heavy. Videos you encounter in real life are much lighter because they aren't stored in float32, and they're typically compressed by a large factor, such as in the MPEG format. Section 2.3. The Gears of Neural Networks. Tensor Operations. Much as any computer program can be ultimately reduced to a small set of binary operations on binary inputs, and, or, nor, and so on, all transformations learned by deep neural networks can be reduced to a handful of tensor operations or tensor functions applied to tensors of numeric data. For instance, it's possible to add tensors, multiply tensors, and so on. In our initial example, we built our model by stacking dense layers on top of each other. A Keras layer instance looks like this. This layer can be interpreted as a function which takes as input a matrix and returns another matrix, a new representation for the input tensor. Specifically, the function is as follows, where W is a matrix and B is a vector, both attributes of the layer. Let's unpack this. We have 3 tensor operations here. A dot product, dot, between the input tensor and a tensor named W. An addition, plus, between the resulting matrix and a vector B. A ReLU operation. ReLU of x is max of x, 0. ReLU stands for rectified linear unit. Note: although this section deals entirely with linear algebra expressions, you won't find any mathematical notation here. I've found that mathematical concepts can be more readily mastered by programmers with no mathematical background if they're expressed as short Python snippets instead of mathematical equations. So we'll use NumPy and TensorFlow code throughout. Section 2.3.1. Element-wise operations. The ReLU operation and addition are element-wise operations, operations that are applied independently to each entry in the tensors being considered. This means these operations are highly amenable to massively parallel implementations. Vectorized implementations, a term that comes from the vector processor supercomputer architecture from the 1970 to 90 period. If you want to write a naive Python implementation of an element-wise operation, you use a for loop, as in this naive implementation of an element-wise ReLU operation. You could do the same for addition. On the same principle, you can do element-wise multiplication, subtraction, and so on. In practice, when dealing with NumPy arrays, these operations are available as well-optimized built-in NumPy functions, which themselves delegate the heavy lifting to a basic linear algebra subprogram, or BLAS, implementation. BLAS are low-level, highly parallel, efficient tensor manipulation routines that are typically implemented in Fortran or C. So in NumPy, you can do the following element-wise operation, and it will be blazingly fast. Let's actually time the difference. This takes 0.02 seconds. Meanwhile, the naive version takes a stunning 2.45 seconds. Likewise, when running TensorFlow code on a GPU, element-wise operations are executed via fully vectorized CUDA implementations that can best utilize the highly parallel GPU chip architecture. Section 2.3.2 Broadcasting. Our earlier naive implementation of naive_add only supports the addition of rank 2 tensors with identical shapes. But in the dense layer introduced earlier, we added a rank 2 tensor with a vector. What happens with addition when the shapes of two tensors being added differ? When possible, if there's no ambiguity, the smaller tensor will be broadcast to match the shape of the larger tensor. Broadcasting consists of two steps. 1. Axes, called broadcast axes, are added to the smaller tensor to match the endim of the larger tensor. 2. The smaller tensor is repeated alongside these new axes to match the full shape of the larger tensor. Let's look at a concrete example. Consider x with shape 32, 10 surrounded in parentheses and y with shape 10, surrounded in parentheses. First, we add an empty first axis to y, whose shape becomes 1, 10 surrounded in parentheses. Then we repeat y 32 times alongside this new axis, so that we end up with a tensor y with a shape of 32, 10 surrounded in parentheses, where y index of I, colon equals y for I in range from 0 to 32. At this point, we can proceed to add x and y because they have the same shape. In terms of implementation, no new rank 2 tensor is created because that would be terribly inefficient. The repetition operation is entirely virtual. It happens at the algorithmic level rather than at the memory level. But thinking of the vector being repeated 10 times alongside a new axis is a helpful mental model. Here's what a naive implementation would look like. With broadcasting, you can generally perform element-wise operations that take two input tensors if one tensor has the shape of this and the other has the shape of this. The broadcasting will then automatically happen for axes A through n-1. The following example applies the element-wise maximum operation to two tensors of different shapes via broadcasting. Section 2.3.3 Tensor product. The tensor product, or dot product, not to be confused with an element-wise product, the star operator, is one of the most common, most useful tensor operations. In NumPy, a tensor product is done using the np dot function because the mathematical notation for tensor product is usually a dot. In mathematical notation, you note the operation with a dot. Mathematically, what does the dot operation do? Let's start with the dot product of two vectors, x and y. It's computed as follows. You'll have noticed that the dot product between two vectors is a scalar, and that only vectors with the same number of elements are compatible for a dot product. You can also take the dot product between a matrix X and a vector Y, which returns a vector where the coefficients are the dot products between Y and the rows of X. You implement it as follows. You could also reuse the code we wrote previously, which highlights the relationship between a matrix vector product and a vector product. Note that as soon as one of the two tensors has an ndim greater than 1, dot is no longer symmetric, which is to say that dot of x and y isn't the same as dot of y and x. Of course, a dot product generalizes to tensors with an arbitrary number of axes. The most common applications may be the dot product between two matrices. You can take the dot product of two matrices, x and y, dot of x, y, if and only if x dot shape of index 1 equals y dot shape of index 0. The result is a matrix with the shape x dot shape of index 0, y dot shape of index 1 surrounded in parentheses, where the coefficients are the vector products between the rows of x and the column of y. Here's the naive implementation. To understand dot product shape compatibility, it helps to visualize the input and output tensors by aligning them as shown in Figure 2.5. In the figure, x, y, and z are pictured as rectangles, literal boxes of coefficients. Because the rows of x and the columns of y must have the same size, it follows that the width of x must match the height of y. If you go on to develop new machine learning algorithms, you'll likely be drawing such diagrams often. More generally, you can take the dot product between higher dimensional tensors following the same rule for shape compatibility as outlined earlier for the 2D case, and so on. Section 2.3.4 Tensor Reshaping. A third type of tensor operation that's essential to understand is tensor reshaping. Although it wasn't used in the dense layers in our first neural network example, we used it when we pre-processed the digits data before feeding it into our model. Reshaping a tensor means arranging its rows and columns to match a target shape. Naturally, the reshaped tensor has the same total number of coefficients as the initial tensor. Reshaping is best understood via simple examples. A special case of reshaping that's commonly encountered is transposition. Transposing a matrix means exchanging its rows and columns, so that x of index I, colon becomes x of index colon, I. Section 2.3.5 Geometric Interpretation of Tensor Operations. Because the contents of tensors manipulated by tensor operations can be interpreted as coordinates of points in some geometric shape, all tensor operations have a geometric interpretation. For instance, let's consider addition. We'll start with the following vector. It's a point in 2D space. See Figure 2.6. It's common to picture a vector as an arrow linking the origin to the point, as shown in Figure 2.7. Let's consider a new point, b, which is equal to 1, 0.25, which will add to the previous one. This is done geometrically by chaining together the vector arrows with the resulting location being the vector representing the sum of the previous two vectors. See Figure 2.8. As you can see, adding a vector b to a vector a represents the action of copying point A in a new location, whose distance and direction from the original point A is determined by the vector b. If you apply the same vector addition to a group of points in the plane, an object, you would be creating a copy of the entire object in a new location. See Figure 2.9. Tensor addition thus represents the action of translating an object, moving the object without distorting it, by a certain amount in a certain direction. In general, elementary geometric operations such as translation, rotation, scaling, skewing, and so on can be expressed as tensor operations. Here are a few examples. Translation. As you just saw, adding a vector to a point will move the point by a fixed amount in a fixed direction. Applied to a set of points, such as a 2D object, this is called a translation. See Figure 2.9. Rotation. A counterclockwise rotation of a 2D vector by an angle theta, see Figure 2.10, can be achieved via dot product with a 2x2 matrix of R equal to this expression. Scaling. A vertical and horizontal scaling of an image, see Figure 2.11, can be achieved via a dot product with a 2x2 matrix S equal to this expression. Note that such a matrix is called a diagonal matrix because it only has non-zero coefficients in its diagonal, going from the top left to the bottom right. Linear transformation. A dot product with an arbitrary matrix implements a linear transformation. Note that scaling and rotation, listed previously, are by definition linear transforms. Affine transforms. An affine transform, see Figure 2.12, is the combination of a linear transform, achieved via a dot product with some matrix, and a translation, achieved via a vector addition. As you have probably recognized, that's exactly the y equals w dot x plus b computation implemented by the dense layer. A dense layer without an activation function is an affine layer. Dense layer with ReLU activation. An important observation about affine transforms is that if you apply many of them repeatedly, you still end up with an affine transform, so you could just have applied that one affine transform in the first place. Let's try it with 2. Affine 2 of affine 1 of x is equal to w2 dot w1 dot x plus b1 plus b2, which is equal to w2 dot w1 dot x plus w2 dot b1 plus b2. That's an affine transform where the linear part is the matrix w2 dot w1, and the translation part is the vector w2 dot b1 plus b2. As a consequence, a multi-layer neural network made entirely of dense layers without activations would be the equivalent to a single dense layer. This deep neural network would just be a linear model in disguise. This is why we need activation functions like ReLU, seen in action in Figure 2.13. Thanks to activation functions, a chain of dense layers can be made to implement very complex, nonlinear geometric transformations, resulting in very rich hypothesis spaces for your deep neural networks. We'll cover this idea in more detail in the next chapter. Section 2.3.6. A geometric interpretation of deep learning. You just learned that neural networks consist entirely of chains of tensor operations, and that these tensor operations are just simple geometric transformations of the input data. It follows that you can interpret a neural network as a very complex geometric transformation in a high-dimensional space, implemented via a series of simple steps. In 3D, the following mental image may prove useful. Imagine 2 sheets of colored paper, one red and one blue. Put one on top of the other. Now crumple them together into a small ball. That crumpled paper ball is your input data, and each sheet of paper is a class of data in a classification problem. What a neural network is meant to do is figure out a transformation of the paper ball that would uncrumple it, so as to make the two classes cleanly separable again. See Figure 2.14. With deep learning, this would be implemented as a series of simple transformations of the 3D space, such as those you could apply on the paper ball with your fingers, one movement at a time. Uncrumpling paper balls is what machine learning is about. Finding neat representations for complex, highly folded data manifolds in high-dimensional spaces. A manifold is a continuous surface, like our crumpled sheet of paper. At this point, you should have a pretty good intuition as to why deep learning excels at this. It takes the approach of incrementally decomposing a complicated geometric transformation into a long chain of elementary ones, which is pretty much the strategy a human would follow to uncrumple a paper ball. Each layer in a deep network applies a transformation that disentangles the data a little, and a deep stack of layers makes tractable an extremely complicated disentanglement process. Section 2.4. The Engine of Neural Networks. Gradient-based optimization. As you saw in the previous section, each neural layer from our first model example transforms its input data as follows. In this expression, W and B are tensors that are attributes of the layer. They're called the weights or trainable parameters of the layer, the kernel and bias attributes respectively. These weights contain the information learned by the model from exposure to training data. Initially, these weight matrices are filled with small random values, a step called random initialization. Of course, there's no reason to expect that ReLU of dot of input comma W plus B, when W and B are random, will yield any useful representations. The resulting representations are meaningless, but they're a starting point. What comes next is to gradually adjust these weights based on a feedback signal. This gradual adjustment, also called training, is the learning that machine learning is all about. This happens within what is called a training loop, which works as follows. Repeat these steps in a loop until the loss seems sufficiently low. 1. Draw a batch of training samples, x, and corresponding targets, y_true. 2. Run the model on x, a step called the forward pass, to obtain predictions, y_pred. 3. Compute the loss of the model on the batch, a measure of the mismatch between y_pred and y_true. 4. Update all weights of the model in a way that slightly reduces the loss on this batch. You'll eventually end up with a model that has a very low loss on its training data, a low mismatch between the predictions y_pred and the expected targets y_true. The model has learned to map its inputs to correct targets. From afar, it may look like magic, but when you reduce it to elementary steps, it turns out to be simple. Step 1 sounds easy enough, just I/O code. Steps 2 and 3 are merely the application of a handful of tensor operations, so you could implement these steps purely from what you've learned in the previous section. The difficult part is step 4, updating the model's weights. Given an individual weight coefficient in the model, how can you compute whether the coefficient should be increased or decreased, and by how much? One naive solution would be to freeze all weights in the model except the one scalar coefficient being considered, and try different values for this coefficient. Let's say the initial value of the coefficient is 0.3. After the forward pass on a batch of data, the loss of the model on the batch is 0.5. If you change the coefficient's value to 0.35 and rerun the forward pass, the loss increases to 0.6. But if you lower the coefficient to 0.25, the loss falls to 0.4. In this case, it seems that updating the coefficient by minus 0.05 would contribute to minimizing the loss. This would have to be repeated for all coefficients in the model. But such an approach would be horribly inefficient because you'd need to compute 2 forward passes, which are expensive, for every individual coefficient, of which there are many, usually thousands and sometimes millions. Thankfully, there's a much better approach: gradient descent. Gradient descent is the optimization technique that powers modern neural networks. Here's the gist of it. All of the functions used in our models, such as dot or plus, transform their input in a smooth and continuous way. If you look at z equals x plus y, for instance, a small change in y only results in a small change in z. If you know the direction of the change in y, you can infer the direction of the change in z. Mathematically, you'd say these functions are differentiable. If you chain together such functions, the bigger functions you obtain is still differentiable. In particular, this applies to the function that maps the model's coefficient to the loss of the model on a batch of data. A small change in the model's coefficient results in a small, predictable change in the loss value. This enables you to use a mathematical operator called the gradient to describe how the loss varies as you move the model's coefficients in different directions. If you compute this gradient, you can use it to move the coefficients, all at once in a single update, rather than one at a time, in a direction that decreases the loss. If you already know what differentiable means and what a gradient is, you can skip to the section 2.4.3. Otherwise, the following 2 sections will help you understand these concepts. Section 2.4.1. What's a derivative? Consider a continuous smooth function f of x equals y, mapping a number x to a new number y. We can use the function in figure 2.15 as an example. Because the function is continuous, a small change in x can only result in a small change in y. That's the intuition behind continuity. Let's say you increase x by a small factor, epsilon underscore x. This results in a small epsilon underscore y changed to y, as shown in figure 2.16. In addition, because the function is smooth, its curve doesn't have any abrupt angles, when epsilon underscore x is small enough, around a certain point p, it's possible to approximate f as a linear function of slope a so that epsilon underscore y becomes a times epsilon underscore x. Obviously, this linear approximation is valid only when x is close enough to p. The slope a is called the derivative of f in p. If a is negative, it means a small increase in x around p will result in a decrease of f of x, as shown in figure 2.17. And if a is positive, a small increase in x will result in an increase of f of x. Further, the absolute value of a, the magnitude of the derivative, tells you how quickly this increase or decrease will happen. For every differentiable function f of x, differentiable means can be derived, for example, smooth, continuous functions can be derived, there exists a derivative function f prime of x that maps values of x to the slope of the local linear approximation of f in those points. For instance, the derivative of cosine of x is negative sine of x. The derivative of f of x equals a times x is f prime of x is a, and so on. Being able to derive functions is a very powerful tool when it comes to optimization, the task of finding values of x that minimize the value of f of x. If you are trying to update x by a factor of epsilon underscore x in order to minimize f of x, and you know the derivative of f, then your job is done. The derivative completely describes how f of x evolves as you change x. If you want to reduce the value of f of x, you just need to move x a little in the opposite direction from the derivative. Section 2.4.2. Derivative of a tensor operation. The gradient. The function we were just looking at turned a scalar value x into another scalar value y. You could plot it as a curve in a 2D plane. Now imagine a function that turns a tuple of scalars, x, y, into a scalar value z. That would be a vector operation. You could plot it as a 2D surface in a 3D space, indexed by coordinates x, y, z. Likewise, you can imagine functions that take matrices as inputs, functions that take rank 3 tensors as inputs, etc. The concept of derivation can be applied to any such function, as long as the surfaces they describe are continuous and smooth. The derivative of a tensor operation, or tensor function, is called a gradient. Gradients are just the generalization of the concept of derivatives to functions that take tensors as input. Remember how, for a scalar function, the derivative represents the local slope of the curve of the function? In the same way, the gradient of a tensor function represents the curvature of the multidimensional surface described by the function. It characterizes how the output of the function varies when its input parameters vary. Let's look at an example grounded in machine learning. Consider an input vector x, a sample in a dataset, a matrix W, the weights of the model, a target, y underscore true, what the model should learn to associate to x, a loss function, loss, meant to measure the gaps between the model's current predictions and y underscore true. You can use W to compute a target candidate y underscore pred and then compute the loss, or mismatch, between the target candidate y underscore pred and the target y underscore true. Now, we'd like to use gradients to figure out how to update W so as to make loss underscore value smaller. How do we do that? Given fixed inputs x and y underscore true, the preceding operations can be interpreted as a function mapping values of W, the model's weights, to loss values. Let's say the current value of W is W0. Then the derivative of f at point W0 is a tensor grad of loss underscore value comma W0, with the same shape as W, where each coefficient grad of loss underscore value, comma, W, index of I, comma, J, indicates the direction and magnitude of the change in loss underscore value you observe when modifying W0, index of I, comma, J. That tensor, grad of loss underscore value, comma, W0, is the gradient of the function f of W equal to loss underscore value in W0, also called gradient of loss underscore value with respect to W around W0. Partial derivatives. The tensor operation grad of f of W, comma, W, which takes as input a matrix W, can be expressed as a combination of scalar functions grad underscore ij of f of W, comma, W underscore ij, each of which would return the derivative of the loss underscore value equal to f of W with respect to the coefficient W index of I, comma, j of W, assuming all other coefficients are constant. Grad underscore ij is called the partial derivative of f with respect to W index of I, comma, j. Concretely, what does grad of loss underscore value, comma, W0 represent? You saw earlier that the derivative of a function, f of x, of a single coefficient can be interpreted as the slope of the curve of f. Likewise, grad of loss underscore value, comma, W0 can be interpreted as the tensor describing the direction of steepest ascent of loss underscore value equal to f of W around W0, as well as the slope of this ascent. Each partial derivative describes the slope of f in a specific direction. For this reason, in much the same way that for a function f of x, you can reduce the value of f of x by moving x a little in the opposite direction from the derivative, with a function f of w of a tensor, you can reduce loss underscore value equal to f of w by moving w in the opposite direction from the gradient. For example, W1 equals W0 minus step times grad of f of W0, comma, W0, where step is a small scaling factor. That means going against the direction of the steepest ascent of f, which intuitively should put you lower on the curve. Note that the scaling factor step is needed because grad of loss underscore value, comma, W0 only approximates the curvature when you're close to W0, so you don't want to get too far from W0. Section 2.4.3. Stochastic gradient descent. Given a differentiable function, it's theoretically possible to find its minimum analytically. It's known that a function's minimum is a point where the derivative is zero. So all you have to do is find all the points where the derivative goes to zero and check for which of these points the function has the lowest value. Applied to a neural network, that means finding analytically the combination of weight values that yields the smallest possible loss function. This can be done by solving the equation grad of f of w, comma, w equal to 0 for w. This is a polynomial equation of n variables, where n is the number of coefficients in the model. Although it would be possible to solve such an equation for n equals 2 or n equals 3, doing so is intractable for real neural networks, where the number of parameters is never less than a few thousand and can often be several tens of millions. Instead, you can use the four-step algorithm outlined at the beginning of this section. Modify the parameters a little by little based on the current loss value for a random batch of data. Because you're dealing with differentiable functions, you can compute its gradient, which gives you an efficient way to implement step 4. If you update the weights in the opposite direction from the gradient, the loss will be a little less every time. 1. Draw a batch of training samples, x, and corresponding targets, y underscore true. 2. Run the model on x to obtain predictions y underscore pred. This is called the forward pass. 3. Compute the loss of the model on the batch, a measure of the mismatch between y underscore pred and y underscore true. 4. Compute the gradient of the loss with regard to the model's parameters. This is called the backward pass. 5. Move the parameters a little in the opposite direction from the gradient. For example, w minus equals learning underscore rate times gradient, thus reducing the loss on the batch a bit. The learning rate, learning_rate, here would be a scalar function modulating the speed of the gradient descent process. Easy enough. What we just described is called mini-batch stochastic gradient descent, mini-batch SGD. The term stochastic refers to the fact that each batch of data is drawn at random. Stochastic is a scientific synonym of random. Figure 12.18 illustrates what happens in 1D when the model only has one parameter and you only have one training sample. As you can see, intuitively it's important to pick a reasonable value for the learning_rate factor. If it's too small, the descent down the curve will take many iterations, and it could get stuck in a local minimum. If learning_rate is too large, your updates may end up taking you to completely random locations on the curve. Note that a variant of the mini-batch SGD algorithm would be to draw a single sample and target at each iteration, rather than drawing a batch of data. This would be true SGD as opposed to mini-batch SGD. Alternatively, going to the opposite extreme, you could run every step on all data available, which is called batch gradient descent. Each update would then be more accurate, but far more expensive. The efficient compromise between these two extremes is to use mini batches of reasonable size. Although Figure 2.18 illustrates gradient descent in a 1D parameter space, in practice you'll use gradient descent in highly dimensional spaces. Every weight coefficient in a neural network is a free dimension in the space, and there may be tens of thousands or even millions of them. To help you build intuition about loss surfaces, you can also visualize gradient descent along a 2D loss surface, as shown in Figure 2.19. But you can't possibly visualize what the actual process of training a neural network looks like. You can't represent a 1 million dimensional space in a way that makes sense to humans. As such, it's good to keep in mind that the intuitions you develop through these low-dimensional representations may not always be accurate in practice. This has historically been a source of issues in the world of deep learning research. Additionally, there exist multiple variants of SGD that differ by taking into account previous weight updates when computing the next weight update, rather than just looking at the current value of the gradients. There is, for instance, SGD with momentum, as well as eta-grad, RMS prop, and several others. Such variants are known as optimization methods or optimizers. In particular, the concept of momentum, which is used in many of these variants, deserves your attention. Momentum addresses two issues with SGD: convergence speed and local minima. Consider Figure 2.20, which shows the curve of a loss as a function of a model parameter. As you can see, around a certain parameter value, there is a local minimum. Around that point, moving left would result in the loss increasing, but so would moving right. If the parameter under consideration were being optimized via SGD with a small learning rate, the optimization process could get stuck at the local minimum instead of making its way to the global minimum. You can avoid such issues by using momentum, which draws inspiration from physics. A useful mental image here is to think of the optimization process as a small ball rolling down the loss curve. If it has enough momentum, the ball won't get stuck in a ravine and will end up at the global minimum. Momentum is implemented by moving the ball at each step based not only on the current slope value, current acceleration, but also on the current velocity, resulting from past acceleration. In practice, this means updating the parameter w based not only on the current gradient value, but also on the previous parameter update, such as in this naive implementation. Section 2.4.4 Chaining Derivatives, the backpropagation algorithm. In the preceding algorithm, we casually assume that because a function is differentiable, we can easily compute its gradient. But is that true? How can we compute the gradient of complex expressions in practice? In the two-layer model we started the chapter with, how can we get the gradient of the loss with regard to the weights? That's where the backpropagation algorithm comes in. The chain rule. Backpropagation is a way to use the derivatives of simple operations, such as additions, ReLU, or tensor product, to easily compute the gradient of arbitrarily complex combinations of these atomic operations. Crucially, a neural network consists of many tensor operations chained together, each of which has a simple known derivative. For instance, the model defined in listing 2.2 can be expressed as a function parameterized by the variables w1, b1, w2, and b2, belonging to the first and second dense layers respectively. Involving the atomic operations dot, relu, softmax, and plus, as well as our loss function, loss, which are easily differentiable. Calculus tells us that such a chain of functions can be derived using the following identity called the chain rule. Consider two functions, f and g, as well as the composed function fg such that fg of x equals f of g of x. Then the chain rule states that grad of x comma y equals grad of y comma x1 times grad of x1 comma x. This enables you to compute the derivative of fg as long as you know the derivatives of f and g. The chain rule is named as it is because when you add more intermediate functions, it starts looking like a chain. Applying the chain rule to the computation of the gradient values of a neural network gives rise to an algorithm called backpropagation. Let's see how that works concretely. Automatic differentiation with computation graphs. A useful way to think about backpropagation is in terms of computation graphs. A computation graph is the data structure at the heart of TensorFlow and the deep learning revolution in general. It's a directed acyclic graph of operations, in our case, tensor operations. For instance, figure 2.21 shows the graph representation of our first model. Computation graphs have been an extremely successful abstraction in computer science because they enable us to treat computation as data. A computation expression is encoded as a machine-readable data structure that can be used as the input or output of another program. For instance, you could imagine a program that receives a computation graph and returns a new computation graph that implements a large-scale distributed version of the same computation. This would mean that you could distribute any computation without having to write the distribution logic yourself. Or imagine a program that receives a computation graph and can automatically generate the derivative of the expression it represents. It's much easier to do these things if your computation is expressed as an explicit graph data structure rather than, say, lines of ASCII characters in a .py file. To explain backpropagation clearly, let's look at a really basic example of a computation graph. See Figure 2.22. We'll consider a simplified version of Figure 2.21, where we only have one linear layer and where all variables are scalar. We'll take two scalar variables, w and b, a scalar input, x, and apply some operations to them to combine them into an output, y. Finally, we'll apply an absolute value error loss function, loss underscore val equals abs of y underscore true minus y. Since we want to update w and b in a way that will minimize loss underscore val, we are interested in computing grad of loss underscore val comma b and grad of loss underscore val comma w. Let's set concrete values for the input nodes in the graph, that is to say, the input x, the target y underscore true, w, and b. We'll propagate these values to all nodes in the graph, from top to bottom until we reach loss underscore val. This is the forward pass. See Figure 2.23. Now, let's reverse the graph. For each edge in the graph going from A to B, we will create an opposite edge from B to A and ask, how much does B vary when A varies? That is to say, what is grad of B comma A? We'll annotate each inverted edge with this value. This backward graph represents the backward pass. See Figure 2.24. We have the following. Grad of loss underscore val comma x2 equal to 1, because as x2 varies by an amount epsilon, loss underscore val equals the absolute of 4 minus x2 varies by the same amount. Grad of x2, x1 equals 1, because as x1 varies by an amount epsilon, x2 equals x1 plus b, which equals x1 plus 1, varies by the same amount. Grad of x2, b equals 1, because as b varies by an amount epsilon, x2 equals x1 plus b, which equals 6 plus b, varies by the same amount. Grad of x1, w equals 2, because as w varies by an amount epsilon, x1 equals x times w, which equals 2 times w, varies by 2 times epsilon. What the chain rule says about this backward graph is that you can obtain the derivative of a node with respect to another node by multiplying the derivatives for each edge along the path linking the two nodes. For instance, grad of loss underscore val, w equals grad of loss underscore val, x2 times grad of x2, x1 times grad of x1, w. See figure 2.25. By applying the chain rule to our graph, we obtain what we are looking for. Grad of loss underscore val, w equals 1 times 2, which is equal to 2. Grad of loss underscore val, b equals 1 times 1, which equals 1. Note: if there are multiple paths linking the two nodes of interest, A and B, in the backward graph, we would obtain grad of b, a by summing the contributions of all the paths. And with that, you just saw backpropagation in action. Backpropagation is simply the application of the chain rule to a computation graph. There's nothing more to it. Backpropagation starts with the final loss value and works backward from the top layers to the bottom layers, computing the contribution that each parameter had in the loss value. That's where the name backpropagation comes from. We backpropagate the loss contributions of different nodes in a computation graph. Nowadays, people implement neural networks in modern frameworks that are capable of automatic differentiation, such as TensorFlow. Automatic differentiation is implemented with the kind of computation graph you've just seen. Automatic differentiation makes it possible to retrieve the gradients of arbitrary compositions of differentiable tensor operations without doing any extra work besides writing down the forward pass. When I wrote my first neural networks in C in the 2000s, I had to write my gradients by hand. Now, thanks to modern automatic differentiation tools, you'll never have to implement backpropagation yourself. Consider yourself lucky. The gradient tape in TensorFlow. The API through which you can leverage TensorFlow's powerful automatic differentiation capabilities is the gradient tape. It's a Python scope that will record the tensor operations that run inside it in the form of a computation graph, sometimes called a tape. This graph can then be used to retrieve the gradient of any output with respect to any variable or set of variables, instances of the tf.variable class. A tf.variable is a specific kind of tensor meant to hold mutable state. For instance, the weights of a neural network are always tf.variable instances. The gradient tape works with tensor operations. It also works with lists of variables. You will learn about the gradient tape in the next chapter. Section 2.5. Looking back at our first example. You're nearing the end of this chapter, and you should now have a general understanding of what's going on behind the scenes in a neural network. What was a magical black box at the start of the chapter has turned into a clearer picture, as illustrated in Figure 2.26. The model, composed of layers that are chained together, maps the input data to predictions. The loss function then compares these predictions to the targets, producing a loss value, a measure of how well the model's predictions match what was expected. The optimizer uses this loss value to update the model's weights. Let's go back to the first example in this chapter and review each piece of it in light of what you've learned since. This was the input data. Now that you understand, the input images are stored in NumPy tensors, which are here formatted as float32 tensors of shape 60,000, 784 surrounded in parentheses, training data, and 10,000,784, surrounded in parentheses, test data, respectively. This was our model. Now you understand that this model consists of a chain of two dense layers, that each layer applies a few simple tensor operations to the input data, and that these operations involve weight tensors. Weight tensors, which are attributes of the layers, are where the knowledge of the model persists. This was the model compilation step. Now you understand that sparse_categorical_cross entropy is the loss function that's used as a feedback signal for learning the weight tensors, and which the training phase will attempt to minimize. You also know that this reduction of the loss happens via mini-batch stochastic gradient descent. The exact rules governing a specific use of gradient descent are defined by the RMS prop optimizer passed as the first argument. Finally, this was the training loop. Now you understand what happens when you call fit. The model will start to iterate on the training data in mini batches of 128 samples, 5 times over. Each iteration over all the training data is called an epoch. For each batch, the model will compute the gradient of the loss with regard to the weights, using the backpropagation algorithm, which derives from the chain rule in calculus, and move the weights in the direction that will reduce the value of the loss for this batch. After these 5 epochs, the model will have performed 2,345 gradient updates, 469 per epoch, and the loss of the model will be sufficiently low that the model will be capable of classifying handwritten digits with high accuracy. At this point, you already know most of what there is to know about neural networks. Let's prove it by re-implementing a simplified version of that first example from scratch in TensorFlow step by step. Section 2.5.1. Re-implementing our first example from scratch in TensorFlow. What better demonstrates full, unambiguous understanding than implementing everything from scratch? Of course, what from scratch means here is relative. We won't re-implement basic tensor operations, and we won't implement backpropagation. But we'll go to such a low level that we will barely use any Keras functionality at all. Don't worry if you don't understand every little detail in this example just yet. The next chapter will dive in more detail into the TensorFlow API. For now, just try to follow the gist of what's going on. The intent of this example is to help crystallize your understanding of the mathematics of deep learning using a concrete implementation. Let's go. A simple, dense class. You've learned earlier that the dense layer implements the following input transformation, where W and B are model parameters and activation is an element-wise function, usually ReLU, but it would be softmax for the last layer. Let's implement a simple Python class, naive_dense, that creates 2 TensorFlow variables, W and B, and exposes a __call___ method that applies the preceding transformation. A simple sequential class. Now, let's create a naive sequential class to chain these layers. It wraps a list of layers and exposes a __call___ method that simply calls the underlying layers on the inputs in order. It also features a weights property to easily keep track of the layers parameters. Using this naive dense class and this naive sequential class, we can create a mock Keras model. A batch generator. Next, we need a way to iterate over the MNIST data in mini batches. This is easy. Section 2.5.2. Running one training step. The most difficult part of the process is the training step, updating the weights of the model after running it on one batch of data. We need to 1. Compute the predictions of the model for the images in the batch. 2. Compute the loss value for these predictions given the actual labels. 3. Compute the gradient of the loss with regard to the model's weights. 4. Move the weights by a small amount in the direction opposite to the gradient. To compute the gradient, we'll use the TensorFlow gradient tape object we introduced in section 2.4.4. As you already know, the purpose of the weight update step, represented by the preceding update_weights function, is to move the weights by a bit in a direction that will reduce the loss on this batch. The magnitude of the move is determined by the learning rate, typically a small quantity. The simplest way to implement this update weights function is to subtract gradient times learning_rate from each weight. In practice, you would almost never implement a weight update step like this by hand. Instead, you would use an optimizer instance from Keras like this. Now that our per batch training step is ready, we can move on to implementing an entire epoch of training. Section 2.5.3. The full training loop. An epoch of training simply consists of repeating the training step for each batch in the training data, and the full training loop is simply the repetition of one epoch. Let's test drive it. Section 2.5.4. Evaluating the model. We can evaluate the model by taking the argmax of its predictions over the test images and comparing it to the expected labels. All done. As you can see, it's quite a bit of work to do by hand what you can do in a few lines of Keras code. But because you've gone through these steps, you should now have a crystal clear understanding of what goes on inside a neural network when you call fit. Having this low-level mental model of what your code is doing behind the scenes will make you better able to leverage the high-level features of the Keras API. Summary. Tensors form the foundation of modern machine learning systems. They come in various flavors of D-type, rank, and shape. You can manipulate numerical tensors via tensor operations, such as addition, tensor product, or element-wise multiplication, which can be interpreted as encoding geometric transformations. In general, everything in deep learning is amenable to a geometric interpretation. Deep learning models consist of chains of simple tensor operations parameterized by weights, which are themselves tensors. The weights of a model are where its knowledge is stored. Learning means finding a set of values for the model's weights that minimize a loss function for a given set of training data samples and their corresponding targets. Learning happens by drawing random batches of data samples and their targets and computing the gradient of the model parameters with respect to the loss on the batch. The model parameters are then moved a bit, the magnitude of the move is defined by the learning rate, in the opposite direction from the gradient. This is called mini-batch stochastic gradient descent. The entire learning process is made possible by the fact that all tensor operations in neural networks are differentiable, and thus it is possible to apply the chain rule of derivation to find the gradient function mapping the current parameters and the current batch of data to a gradient value. This is called backpropagation. Two key concepts you'll see frequently in future chapters are loss and optimizers. These are two things you need to define before you begin feeding data into a model. The loss is the quantity you'll attempt to minimize during training, so it should represent a measure of success for the task you're trying to solve. The optimizer specifies the exact way in which the gradient of the loss will be used to update parameters. For instance, it could be the RMS prop optimizer, SGD with momentum, and so on.